Well, welcome back. My name is Al Romick. I am the Executive Officer of the National Academy of Engineering. I'm a member of our aerospace section. I've been in this role for about 10 years. Prior to that, I was the VP and General Manager of the Lockheed Skunk Works, and prior to that, served at NAE National Labs, ultimately as the Deputy Lab Director there. But welcome all here today. As John said, this is our inaugural convocation, so this is a big experiment. And we're excited to welcome you to the Beckman Center today. What we have up next is a group of excellent panelists to discuss various aspects of innovation. Once again, moderated by Deanne Bell, who you were introduced to earlier. And very briefly, in addition, serving in the panel, we have Jose Reyes, who is the Chief Technology Officer and co-founder at NuScale Power, who will discuss energy and small modular reactors. We have Mike Musallam, who is the co-founder of the Linda and Mike Musallam Foundation to discuss innovations in medicine and life sciences, the former founder and CEO of Edwards Life Sciences. We have Lori Leshin, who is the director of the NASA Jet Propulsion Laboratory at Caltech to discuss advances in space exploration. And finally, Sujay King Liu, Dean of Engineering at Cal Berkeley, to discuss quantum devices, and of course, our incoming president. And so with that, I'd like Deanne and the panelists to come to the stage and start the festivities.
All right. The end. There's no particular order, whichever. Sure. Yeah. All right, hello. Is this working? I will be better at keeping it up close. I'm used to having a lav. Well, welcome again, everyone, to this wonderful, exciting panel. I know I'm really excited to dive into engineering innovation for a brighter future, and we're going to be doing a mini dive into all these different sectors to really look at innovation across, the breadth of engineering. We're going to be talking about energy and small modular reactors with Jose. Next, we'll be talking about innovations in medicine and life sciences with Mike. Then we're going to be learning more about advancements in space exploration with Lori, and also diving into quantum devices and computing with Sujay. So the way it's going to work today on this panel is each of our speakers are going to be going up to the podium, and they're going to give a little small presentation so you can get entrenched in their work and in their knowledge. And then at the end of our presentations, we'll open it up to a Q&A. So if you have any questions, just put those in the back of your head, and there'll be an opportunity for us to pass the microphone around again. So thank you, everyone, for being here. Thank you to our presenters for being here today. Our first presenter today is going to be Jose Reyes Jr. He's the Chief Technology Officer and co-founder at NuScale Power. Jose Reyes Jr. is an NAE member and co-founded NuScale Power LLC, co-designed the NuScale passively cooled small nuclear reactor, and is an internationally recognized expert on passive safety system design, testing, and operations for nuclear power plants. Jose, we look forward to hearing your presentation.
Thank you very much. It's an exciting time right now to be looking at energy. It's an area that continues to grow. The demand continues to grow. And it really is my pleasure to be here today with you. I feel a certain connection. It wasn't, well, it was long ago that I was an early career faculty member, quite a while ago. But for me, it was an opportunity to start developing some innovative research. And in particular, I've always been an energy researcher. I started my career with a small grant. This is at Oregon State University, as an assistant professor. My grant was for $4,000. Let's give you a sense of how long ago it was. You can actually do something with $4,000. And it's been exciting to the development over time of where we are today. My goal back then was to come up with a passive safety system that could make nuclear power safer, simpler, easier to deploy, and that was way back when. And so from that small $4,000, we've leveraged to create the NuScale Power. So I co-founded that in 2007 with the idea of commercializing a small modular reactor. And it's now listed on the New York Stock Exchange. which is exciting to me. Under the ticker symbol SMR. And I think, I haven't checked today, but I think our market cap's somewhere around $6 billion. So a lot of interest in nuclear power, especially in small modular reactors. Just by a show of hands, how many of you are doing some energy-related research? Oh, quite a few. That's great. That's good. Good, because we need it. Energy demand just continues to increase. And it's becoming clear that we need an abundance of clean energy, clean, reliable energy. And we need it now. If you look at the population growth of sometime by 2050, we're looking at almost 10 billion people globally. The bulk of the energy demand comes from emerging markets, developing economies. And while we typically think of electricity and for lighting and heating and cooling, that often gets the most attention. The energy needs of the industrial sector often gets overlooked. So manufacturing, mining, construction, agriculture are all industries that need clean energy options. Chemical manufacturing accounts for about 40% of the manufacturing energy needs. Most recently, and this is interesting to me because 3 or 4 years ago, we were talking to data centers, and they said, well, we need 50 megawatts, 100 megawatts. Today, they're coming to us, we need 1,000 megawatts, we need 2,000 megawatts. Huge increase in the need for energy. So that's exciting to see. But given all these demands, we need to work together. All types of energy, all forms of energy, we're looking for ways in which we can provide that clean, reliable energy. And so I'm looking forward to working with you on how we can innovate some new energy systems. So that brings me to the NuScale small modular reactor. What is that? So in this image here on the left-hand side is one of our modules. It's manufactured in a factory, and it includes everything. It includes the reactor vessel as well as the containment vessel. Instead of the big concrete domes that you're used to when you think about nuclear, we replaced that big concrete dome with a relatively small steel containment. And then inside that sits the reactor. Everything you need for safety is in the reactor. Everything you need to produce steam is right there in that module. And during normal operation, that module sits in a pool of water. The fact that it's factory manufactured is a big transition because we can ship it, manufacture it in a factory, ship it by truck, rail, or barge to the site, depending on location. And so it becomes an installation instead of an actual construction of the nuclear portion of it. Each module produces 250 megawatts thermal, about 77 megawatts electric, and we can go with 4 modules, 6 modules, 12 modules, whatever the customer requires, but you can add them incrementally. We designed it for a 60-year life, and the biggest thing is the safety. Under worst-case conditions, the reactors will shut themselves down, and with no operator action, without the need for any AC or DC power, and they remain cooled for an unlimited period of time without the need to add water. So this is the fundamental aspect of our design is this new level of safety. And because of that, we received our design certification from the US Nuclear Regulatory Commission. So we are the only small modular reactor to have been approved by the NRC. And so we're excited about that. We have 6 of the modules currently in production at facilities at Doosan in South Korea. The other big thing is we've got this site boundary EPZ. Again, because of the safety levels, we can actually meet all the requirements for safety at the site boundary, as opposed to a 10-mile radius, which is currently required for nuclear power. So when you see the large nuclear power plants, they're required by law to have an evacuation zone that's 10 miles in radius, with sirens and all types of things. That's completely eliminated for our design. Again, we meet all those requirements that you would meet at 10 miles, we can meet it at the fence. So it's a big step forward for nuclear. It's also a new approach to manufacturing construction. It's really a very different look at nuclear. And I don't see a clock here, so I'm gonna just keep on talking. Oh, 11:11. Oh, so okay, there we go. I was looking for the countdown and a hook, you know. So this is a new approach to deploying nuclear power. Early on, we saw that there was a tremendous need for this. By manufacturing your modules in a factory, a well-controlled environment, and in parallel doing your civil construction, you drop your construction schedule from roughly 6 years to about 3 years. Significant improvement, and that's for the first of a kind. So we think we can do better once we build a few. So that's a big step forward in terms of nuclear power. Of course, the advantage of nuclear power is it's carbon-free, it's reliable, 24/7 type power. So we have our forgings, we make our vessels, then we can ship them to the site, and then it's an installation process into an existing building, and it sits in a pool of water. Because of again, the safety of the design, we're the only commercial nuclear power plant that's been approved for off-grid operation. Currently, all nuclear power plants are required to have 2 independent connections to the AC grid. And the reason they need that is because they need AC power for their pumps and to move water around. In our design, we don't need any AC or DC power to keep the plant safe. A big step forward. But that off-grid operation allows us then to be placed closer to the end user. So I think this past year we talked to 11 different oil and gas companies, clean chemical companies, who are looking for dedicated power for their processes. And because we can operate off-grid, we can actually be in the proximity of their plants. And because we have a site boundary emergency planning zone, they're not in our emergency planning zone. So that's a big step forward for nuclear. It's an entire new market. And so that's something we're looking at very carefully. We worked on looking at oil refineries. We looked at a project where we have 8 of our NuScale modules connected to a 250,000 barrel per day oil refinery. We could reduce carbon emissions by 200 metric tons per hour. That's a huge reduction in carbon emissions. Hydrogen production, connection to solid oxide electrolysis cells. In that system, we can produce about 50 tons of hydrogen per day per module. Desalination, we looked at water. This is such a huge need. When we look globally at the needs for clean water, it really is water and energy. That nexus is really important. So for desalination, 1 module connected to a reverse osmosis system could produce about 77 million gallons of clean water per day. So 4 modules would be enough for a city of about 4 million people, just to give you a sense of scale. We have worked with renewables to see if we can do load balancing. So we have added parts of our design allow load following to work with renewables. Mission critical facilities, because you have a multi-module approach, you can provide very high levels of availability. So we did a study that we published with Oak Ridge National Lab for their critical infrastructure. What we found was that we can get 99.999% of availability, working with other power productions in the area. And last but not least is our data centers. The fact that there's such a tremendous need for power with these data centers. I'm excited to learn more about the energy systems that you're working on, because I'll probably learn something new, I'm sure. So 17 years ago, I saw the immense positive potential of SMR technology. We believe that we want to provide clean nuclear power to produce electricity, water, and heat to improve the quality of life for people around the world. And that's something that's near and dear to my heart. If you talk to any one of our folks at NuScale, they'll tell you they're mission driven. And we're on a mission, and we're excited about it. With our plants targeted to operate here beginning the end of this decade, we believe we can make some meaningful progress towards providing abundant clean energy. And we believe that this will be energy that will improve the quality of life for people around the world. So I wish you the very best as early career faculty, and look forward to working with you together as we innovate our energy future. So thank you very much.
Thank you, thank you. Wonderful presentation. And next we are going to look at life sciences and innovations in medicine and life sciences. So Mike Masalem is the co-founder of the Linda and Mike Masalem Foundation. Mike is an NAE member, is the co-founder of the Linda and Mike Masalem Foundation, along with his wife, Linda. Previously, Mike served as chairman and chief executive officer of Edwards Life Sciences for more than 20 years and served in industry leadership positions. I should note that there's full bios for all of our speakers in your program, but at this point, I'll give it over to you. Please take the stage.
Thanks very much. Really my pleasure, an honor to be here. I'm totally humbled by this. I mean, really cover life sciences and medicine in 8 minutes. It's staggering. You're going to see it through Mike's point of view, and I've had a chance to sort of live a career in that, and been on every step of the ladder, and I've learned a lot. And You know, what I love is looking at it through the lens of innovation, because I became a student of innovation and really a believer that that's where success lied. That's what separated those that make a difference from those that didn't make quite as big a difference. And I believe that we're in this unbelievable golden age, right? If you think about the way our healthcare exists today, compared to our parents or our grandparents, dramatic, unbelievable, right? The things that happen to us routinely. And we say, wow, that's staggering. Is that over? What do you think? So when you look further ahead, is it going to go fast? Is innovation going to go faster or slower? Every reason to believe it should go faster, right? So what we're able to do in medicine and life sciences and healthcare in general should be dramatic. Now, having said that, and it's inspiring to think about, improving there, wow, the odds are that most people that go into this fail. It's hard. It's really hard, and it starts with kind of the needs analysis, if you will. And I'm not going to use slides here because I'm not sure it can reduce it to that. But understanding the needs is kind of the first job of the innovator. And I think when innovation really gets exposed directly to the needs rather than through a second or third party, it's what speeds up the innovation process. And so I love it when innovators are, especially in healthcare, when they're exposed to patients and the real patient problems, not hearing it third hand through the head of the medical department. Good things happen because the people that are living in the current medicine, they sort of see our world as it is today. They say, can you make this sharper? Can you make this smaller? Can you make this faster? And they don't necessarily step back and rethink the problems that they're involved in. And technology is a big part of it, but it's also just the way we think about improving healthcare, whether it's prevention or care pathways or decision trees. There's a lot of ways to dramatically improve healthcare. And there's something magic that happens when young, bright minds get exposed to experts as well, right? Whether it's a special mentor or somebody that has lived a career of discovery and gets a chance to share it with the bright mind. But it's interesting, it's not always that expert that passes the knowledge down, but it's a lot of times a fresh mind with a fresh idea that stimulates something that nobody thought of before, and so it's powerful. To be successful in healthcare, some of it is driven by what your goal is. I mean, I'm not an academic, but if you're in the academic world, if you could have such a fresh idea that you actually got published, powerful stuff. Or what if you got published in New England Journal of Medicine or achieved a Nobel Prize? I mean, wow, right? That's staggering and that's earth-shattering stuff. There's a lot of folks on the commercial side that said, oh, I'm doing this because if I get this right, we could be rich, right? Our company could get big, it could get bought, it could get sold, good things are gonna happen for me and my family, and everything in between. But, at its core, it's doing something good for mankind that creates the value. And that's what really ends up driving us, those things that I think about, and I had a chance to experience this in my own career, is, okay, can you come up with an innovation that extends life? Can you come up with an innovation that improves the quality of life? Can you come up with an innovation that saves money? Can you come up with the triple win? Extend life, improve the quality of life, and save money. Ding, ding, ding. Now you've really done something powerful. And I was fortunate to have experienced one of those, and there's something special there. Once the idea begins, or once the great idea is there, reducing it to practice is often a lifetime of work, maybe more. It's serious stuff. It's tough because humans are filled with so many variables, right? We're each snowflakes, if you will. And so having one solution that's going to work for billions of people is not trivial, and you don't find that out until you get into it, right? You see a positive spark and it inspires you, but when you start going down the road to really make it happen, it turns out that you need this thing called evidence to really change the practice of medicine. And that's elusive and difficult. You start out with, proving it obviously in the laboratory, but then do you have the courage to actually take it to people and bring your innovation to people? And then you do that in a very careful way such that you're only doing safety studies, not really trying to cover efficacy. And you're learning along the way, wow, it works well in this population, but not on that population. Okay, how do I design a study that's good enough to get this actually approved or get it actually paid for? And that's a gigantic accomplishment just to go through that gauntlet. But then there's some point where you say, okay, can you get every doctor around the world to get the same results that you got in your clinical trial, where everybody in the clinical trial was a rock star? So all those things are really interesting challenges. You learn that engineering and science is a very powerful part of it, but it's a team sport, and you kind of need a team to make it across. And I think, as we say, mindful of what it takes for innovations to really reach practice, it's one of the key parts of it. I think it starts obviously with great science, but it takes a lot of time and a lot of money and a lot of commitment. You're going to have a lot of failure that you face along the way, and the courage to raise your hand and say, I was wrong, but I know my way through this. And you dust yourself off and you make an adjustment and you go, and you get knocked down again and you go again. And it's that kind of commitment that ends up driving, a world of change in the whole field. So when you get to this wonderful world where you can actually make something sustainable, so your idea is so good that people are willing to, pay value for it, and you can take that value and reinvest it in innovation, then you get the machine going, right, where you really create an innovation model. So I'm going to keep it at this very high general level, but I welcome your questions and thoughts. Thank you.
Well, thank you so much, Mike. Thank you. And the next topic is going to be advancements in space exploration. And we have Lori Leshin, director of NASA's Jet Propulsion Laboratory. Lori is a distinguished geochemist and space scientist. She currently serves as director of NASA's Jet Propulsion Laboratory, as well as vice president and Bren Professor of Geochemistry and Planetary Science at Caltech, which manages JPL for NASA. In this role, Leshin oversees Earth and space science research, technology development, and more than 40 active missions in Earth science, astrophysics, planetary science, and beyond. Prior to leading JPL, Leshin was president of Worcester Polytechnic Institute, served as Rensselaer Polytechnic Institute School of Science dean, and held senior executive positions at NASA. All right, I can't wait to hear your presentation,
All right,
Lori.
thank you. Thank you so much. This reminds me of being up here. Well, first of all, it's great to be here. I just came back from DC at 10 o'clock last night. You have no idea how great it is to be here. No comment, that's all I'll say, unless some of you ask. This does remind me of a panel I was on when I was president of WPI Worcester. You pronounce it perfectly, by the way. People in California almost never pronounce Worcester perfectly, so that was well done. With a colleague president from another university who was a neuroscientist, and I'm a space scientist. And we were talking about something, and I was like, well, it's not rocket science. And she said, well, it's not brain surgery. And so I feel like we've got all the bases covered up here on this panel. It's great to be here with great young minds, some of us who aren't such young minds, but I completely agree that it's that matching up of different experiences and different capabilities where magic can happen and magic teams can form. And I'm fortunate to be at a place that lives and thrives on magic teams at JPL. Like, that is kind of our whole vibe. We are constantly pushing the boundaries of what's possible in space. It is a very exciting time in space exploration. Don't know if you've noticed. Here in LA especially, it's an exciting place to be right now. There's, of course, our up in Pasadena, where we are building next generation of space payloads, and our colleagues down at SpaceX in Hawthorne. And then my supposition is, like, every former SpaceX employee now has a space startup somewhere in LA. And so it's a super exciting time in the space business. So I'm just gonna say three things to kind of frame up the innovation story. So one, pretty exciting time in the launch business. So launch innovation and the sort of new commercial entrants, whether that's our pals at SpaceX, this is from down in Texas, catching the booster when it comes back, dang. And huge congratulations to our colleagues at Blue Origin, who had their first successful orbital flight just a month ago. They have bent the curve in terms of access to space, in terms of launch costs. And it just used to be that the cost of getting out of this gravity well was so high that it drove everything about the way we thought about what you put on top of the rocket, which, by the way, at JPL, in spite of our name, propulsion, we really don't do much of the rockets anymore. We used to, but now we're really focused on that thing that's on top of the rocket. This bends that curve. It changes the equation for how we think about what we send to space. It is early days in things like Starship, but even just Falcon 9s and Falcon Heavies, there are over 100 SpaceX launches last year, over 100 launches in 1 year. Think about it. Every 3 days they were launching something. It's amazing. And we fly on those rockets all the time, and those have bent the curve in terms of access to space. So this is an emerging part of the space ecosystem. And by the way, these are the two big guys, right? The two big launch vehicles. Also, the smaller launch vehicle market is really, I was going to say exploding. We don't like to use the word exploding in the space business. Expanding rapidly, even that sounds bad. Anyway, it's growing a lot. So it's a very exciting time in launch, and that drives how the rest of us think about what we want to do in space. I have to give a shout out to the innovative missions that we're doing at JPL, but it's not just us. Again, I have a captive audience, so I get to brag on our teams a bit, but there's so much happening in space these days. And by the way, there's a ton happening in sort of commercial space payloads, the impact of Starlink, and in military space, the creation of Space Force, and the whole great power competition with China in space is fundamentally continuing to shift the space landscape in the near Earth realm quite a lot, and that's going to be very exciting to be a part of in the coming years. But we live for the big science questions. That's what we're all about at JPL. And the innovation derives our ability to answer the biggest, most challenging questions with space missions. And the one that I'm most excited about, and here comes my confession, I'm not an engineer, I'm a scientist, is, are we alone in the universe? We stand on the precipice of being able to answer that question. And frankly, we're in a bit of a space race with ourselves about how and where to answer it. And here are just 3 examples, and I don't have time to tell you lots about each of them, but the question is, are we gonna find evidence for life on a planet orbiting another star that is in another solar system? For that, you need advanced telescopes like the Nancy Grace Roman Space Telescope, getting ready to launch in about 2 years, currently being integrated by our colleagues at Goddard Space Flight Center, but they just installed on the Roman telescope a coronagraph instrument which blocks the light of the star, like I wish I could block the light of this bright light in my face, so that I can see the much dimmer planets that are orbiting that star. We've discovered over 5,000 planets orbiting other stars, but we've discovered essentially all of them, not directly, but by the impact they have on their parent star. The gravity shoves around that parent star, the light gets blocked by the planet as it goes around. What I want is family portraits of other solar systems. I want to take the light from those planets and spread it out and understand the chemistry of those planets. For the first time to start accessing planets more like our own, not quite as small as Earth with this coronagraph, but we're going to be able to do that with the Roman Space Telescope. It's a huge advance in our ability to directly sense extrasolar planets. And then in our own solar system, is it going to be on an icy moon like Jupiter's moon Europa with an ocean that has 2 Earth oceans worth of liquid water? The best place, we think, in the solar system for the possibility of extant life today. We just launched a mission called Europa Clipper back in October that is going to characterize the habitability of this ocean world right in our own solar system. So that's part of this space race. And finally, Mars. If you want to think about the time on Earth when life got started, the place in the solar system that's most likely to preserve evidence of that time, frankly, preserves it better than it's preserved on Earth. It's Mars. That first billion years of terrestrial planet history is fabulously preserved on Mars. And today, our fabulous Perseverance rover, which we were just connecting on how that rover got named. You should tell the story in the Q&A. is traveling around the surface of Mars, collecting incredible rock samples that we are getting ready to return to Earth to study in laboratories and universities across this country and around the world to be able to answer that question about, did life start on Mars around the same time it started on Earth, ancient microbial life? And we have great samples that may well have ancient biomarkers in them, but we won't know until we bring those rocks back. Percy's carrying around, currently has about over 20 little sample tubes filled with rock cores. They're underneath the belly of the rover. It's an incredibly complex robotic system. So excited to all these different ways of trying to get at this question, are we alone? One of the biggest I think we can ask as humans. And what enables this? So at JPL, it's not just about the missions, it's about the science, but it's also about the technologies that emerge to allow us to ask that next harder question. So we're always not only thinking about the missions of today, but the missions of tomorrow that are enabled by the work that we're doing in developing the latest technologies. And just two examples that I'll give. And again, there are many, and these are all done collaboratively with universities, with industry. Imagine what Europa Clipper is going to find. It's an orbiter, so it's not landing on Europa. It's going to map out how thick the icy shell of Europa is. Hopefully, it's going to find some places where that ice thins and perhaps geysers come out, or we might be able to access that ocean if only we could land on the surface and snuggle down there and get in and swim around. We're developing not only the robots that can do that, but the autonomy for those systems that can allow them to make smart decisions in real time. Because you're not joysticking a snake on Europa from Earth. You're not even doing that with our rovers on Mars. We have recently updated Perseverance's software to have much more autonomy to make its own plan for the day. We say, hey, here's 5 things we'd like to do. You figure out the order you want to do them in. You figure out how to do it, right? So we're pushing autonomy here. AI is next, but that drives things. If you think about it, it drives space compute. It drives the systems that we fly and their reliability. So there's all kinds of things that when you really try and think about how to answer these really hard questions, you end up pushing the technology. And the last one I'll mention is quantum. So we hear a lot about quantum and AI these days. Space is full of opportunity for both. We have currently an experiment up on the International Space Station called the Cold Atom Lab, which produced the first Bose-Einstein condensate in 0G. Imagine being able to study what those atoms are doing when they're free floating in space. It's really an incredible opportunity to really understand the quantum nature of matter. We just launched another experiment up to the space station, which will test quantum communications technology. And so we're working towards both quantum sensing and quantum communication in space. And that is going to be a really next level opportunity for us. So there's no shortage of excitement. There's no shortage of great science questions to pursue and great technology to drive. And I look forward to our conversation about exciting times in space. Thanks.
All right, and our next topic is going to be about quantum devices and computing. And we have Soo-Jae King Liu, the Dean of College of Engineering at Berkeley, at UC Berkeley. Soo-Jae is an NAE member and is the Dean of the College of Engineering at UC Berkeley. Her research activities and interests in nanometer scale computing and memory devices with an emphasis on advanced materials, process technology, and structures for energy-efficient electronics. She's also slated to be the next president of NAE, which I know John mentioned earlier today. So join me in welcoming Soo-Jae. Go ahead and take it away.
Thank you, Dan, and thank you all. It's wonderful to be here at this inaugural convocation. I'm really excited always to see early career engineers. They inspire me to continue to do the good work that we're all working towards to benefit humanity ultimately. Now, I was asked to talk about quantum devices and computing. My background really is in computing, but more traditional digital computing. But I think it's good to see how digital computing has developed over the last several decades to provide context for the challenges that still lie ahead for quantum computing. All right, so today, as you have seen yourself personally, and we also see in the talks that happened previously, we live in a digital information society. We're living in the information age. And this is possible because of advancements in computing and data collection. So today, the number of people in the world, I think a previous speaker was saying, is approaching 10 billion, but the number of devices, smart devices in the world is far exceeding the number of people, and that trend is only going to continue within the next several years. By the end of this decade, there'll be dozens more smart devices in the world than humans. So it's not surprising that a lot of the data that's collected and communicated today is actually generated by things, not by people. So this chart shows the amount of data generated every year over the last 10 years, and it's expected this year, so it's rapidly growing, and by the end of this year, we expect the rate of data generation to exceed 150 zettabytes per year. A zettabyte is 1 billion gigabytes, is that right? Terabytes, 1 billion terabytes. And just for reference, for the younger people, a terabyte is roughly equivalent to 40 minutes of video on YouTube. And it turns out that people generate a lot of YouTube videos, so that's a major way of generating data. But more than about 7 years ago, the amount of data generated by things surpassed the amount of data generated by people. And you can see from this chart, most of that data is generated by Internet of Things. And Internet of Things technology touches upon all sectors of economy today. Now, with all that data, it's not useful if you want to derive some artificial intelligence if you don't have the ability to compute and perform, to process information in a time-efficient manner, right? You have to have real-time decision-making. And so information and communications technology advancements over the last 120 years, actually, on this chart, which plots the computational capability, so calculations per second per dollar over the last 120 years. So with exponential improvements in the ability to compute and information, we've been able to see the advent of generative AI systems like ChatGPT. So it's not going to be much longer before the capabilities of computing systems will reach the capabilities of the human brain. But one thing I wanted to point out here is that the complexity of computing systems, computing devices the reason why we're able to compute so many more instructions per second is because the complexity of computers has increased. So the most advanced chips today have over 100 billion transistors. Those are elements just on a chip of silicon the size of your palm. And you can imagine data centers, how complex those systems are. So managing complexity is a theme that I'll come back to towards the end of my introductory talk. Now, looking forward, projecting into the future, which is what researchers do, we see a lot of opportunities or challenges, and this includes new ways to gather more information about the world around us, about life, about the cosmos. So there are opportunities for new sensing devices, including quantum. But then how are we going to store and manage all of that data? It's not going to be easy to come up with cost-effective, high bandwidth and easily communicating memory, data stored in memory, and how do you get that data moved between memory and computers? That is a big challenge if we really want to see this exponential growth in information and communication technology. And today it turns out that with the Internet of Things, you're collecting a lot of data, let's say in autonomous vehicles, but let's say if your vehicle has to communicate with the cloud to do some computations to figure out if the car is going to make a safe move. Well, communication, the speed of communication, the bandwidth and so on, that can limit the ability of artificially intelligent systems in the future. So there's definitely a need to continue to make improvements in communication speed and energy efficiency. And of course, with all this data permeating and information and communication technologies permeating every aspect of modern life, we care about privacy, security of the information that we generate and we rely on. So there's a lot of challenges for security, and this is where quantum could help or actually make systems less secure. So this is something that we all need to think of. And what was mentioned earlier by Dr. Reyes, energy efficiency of computing devices has come to the forefront. You might have seen lots of articles in the last year or so about companies like Amazon and Google planning to purchase lots of power. They decide where to site their data centers based on power availability and the cost of electricity. And of course, small nuclear reactors, modular reactors can be part of the solution. But ultimately, we can have generate more energy to power more computing, but computing itself is actually, there's orders of magnitude improvement possible. If most of the electricity, well, at least half the electricity used in a data center today is used for cooling because the chips heat up when they're doing the computations. Well, if we just get rid of the need for cooling, can we just make more energy efficient chips? This is one of the grand challenges for the computing industry today, and quantum is part of the solution, but can't be the whole solution. In the past, when I've talked with, let's say, CEOs of quantum hardware companies, they say most likely quantum computing devices will be used together with existing digital computing devices. They might be accelerators, so they're going to coexist. So this is why we have to think more holistically. So how do we improve the energy efficiency and the performance of digital computing? There are all kinds of ways that opportunities for researchers to address this. We can come up with more energy efficient transistors. We can reorganize the way we put memory and computing together, so compute in memory or compute near memory chip architectures, and completely different computing paradigms. So rather than the classic von Neumann computing architecture, people are looking at neuromorphic computing. But there's something also called icing machines that I think is quite interesting. It turns out that you can map combinatorial optimization problems to physical systems, and naturally, when you energize the system, it'll reach a ground state of minimum energy. So that's a really quick way to, with energy efficiency, reach a solution for combinatorial optimization problems. And of course, quantum computing can definitely solve some problems that are not tractable today with digital computers. But generally, at least in the computing industry, people think that, yes, quantum computing was definitely going to be helpful to solve some problems much more quickly and more energy efficiently than digital computers, but not every single problem. So this is why we have to think about co-innovation with digital computing. I forgot to mention, this chart shows the rate, the line shows the rate of energy consumption by computers, or for computing data centers over time. And the top yellow curve shows the total amount of energy generated in the world. And you can see that those curves are going to intersect, which doesn't make sense. So again, we have to bend the curve. In computing energy consumption, we need these innovations to bend that curve. And so coming back to complexity, today's computing systems are so complex. In order to design them, for the engineers to even grasp how to design the next generation of a computing hardware, you have to divide the problem up into layers of abstraction, from the transistors to the circuits to the architecture to the algorithms, the software, and the applications. And so it can easily take 10 to 20 years for a new innovation in technology to make it into production. And if we want to speed that cycle of innovation and commercialization up, we need to collaborate across multiple layers of this technology stack, which involves multidisciplinary collaboration and collaboration between software and hardware innovators. So that's really going to be a theme for digital computing as well as for quantum computing. So in recent weeks, we've actually seen milestones reached for quantum computing hardware. What's missing now is quantum software. That's an opportunity for new innovations to accelerate computing to support all of the wonderful discoveries and technologies that my colleagues here have already given us a glimpse, a vision into. So thank you, and I look forward to your questions.
Thank you, Sujay. Thank you to all of our panelists for being here and for giving those wonderful presentations to kick things off. We have about 30 minutes for questions, and I just want to echo actually something that Mike said about that there's so much value in the dissemination of information of all these presentations you just saw, but there's also so much value in the fresh ideas and the new perspectives and the questions from our early career engineers and all of those ideas. So I'm really excited for this Q&A and for us to have that exchange. Jose, I know you asked our audience to raise your hand if you were in energy, but I just want to gauge a little bit of the audience as well. So who in the audience works in life sciences, medical, health sectors? Okay, great. Who in the audience works in air? Or I don't fit in one of those molds. Anyone? Yeah, we got some making their own box. I like it. Great. So that gives us a little gauge of our audience. So I'm going to kick things off with the first question, which is, in the spirit of kind of looking forward, our previous fireside chat, I know that Francis had mentioned, I envision a world where we can hit a button, we have a genetically coded, enzyme. What excites you most about the future and your field? Whether it's, maybe not excites you the most, what's something that excites you about a future advancement, a future milestone, or something that, we're trying to pursue in your respective fields? Who wants to go first? Anyone? Yeah, go ahead, Jose.
Yeah, no, this is an exciting time in terms of energy. And when I think about nuclear in particular, crossing over into other fields, currently nuclear has always been looked at as electricity. But the ability to now produce steam for different processes, as well as clean water through desalination, I see that as a really big opportunity to start decarbonizing, really hard to decarbonize sectors of energy. So to me, that's very exciting. And so I'm looking forward to see who will break first from one of those industries to start talking more about nuclear. So yeah, that excites me.
Great.
Yeah, interesting. Probably nearer term is the power of artificial intelligence and the impact on medicine will be significant. To think about being able to upskill the world, if you will, which AI has the potential of doing, it has a chance to be remarkable. But probably the most fundamental changes are going to come in us understanding the whys behind many of our diseases, our treatments, and our understanding the genetics that we're born with and the environment we live in. We really don't understand the core. We don't have a core understanding of some of the most basic precursors to what we end up experiencing and treating. And so that's going to be super exciting because as we understand them, we're going to be able to treat and diagnose and make a difference earlier.
Great stuff. Yeah, Lori.
It's hard to
Hard
pick.
to pick one.
But I don't know, is that on? Okay, it's on. Oh, there we go. Hi. So I am excited about answering this question that I talked about. I really do. I was in my office 3 months ago, and I got an email from our lead scientist on Perseverance, and it basically said, "We think we found a biomarker. We should talk about it." I was like, wow, you don't get that email every day, like I love my job. It's really cool. And again, it's an ancient potential biomarker that they found with Perseverance, and we sampled the rock, and it's now in the belly of the rover, and we need to bring it back. But we will, one of these avenues is going to give us, we're on the path to answering this question, and it is one that I think changes humanity's view of itself. And so that to me is very exciting. I would say the other thing that will change humanity's view of itself is when more humans get to go up into space and actually get the overview effect and see, kind of see our planet from more for what it is in its context in the universe. And I think there are opportunities through space exploration to have dramatic shifts in human perspective. We saw that when the Apollo 8 astronauts went to the moon and looked back on the Earth with Earthrise. It coincided with the emergence of the modern environmental movement. There are things that space can unlock that are so exciting. So more than a technology, it's really about what space does for humans.
Great stuff. Sujay.
Well, I was thinking with the earlier, I'm going to call it flower side chat, the media is so influential in our society today. So, today we live in the age of AI, and entered that age. But in order to realize ambient intelligence, like in Iron Man, right, when he's just like gesturing, talking to things, and like our surroundings actually can respond to us and know, so we don't have to carry devices or wear devices. I think that's the next frontier. And yeah, I mean, people couldn't imagine what like a personal computer would be useful for decades ago. I think same thing. It's hard for us to imagine what is going to be possible with ambient intelligence.
Great stuff. Great answers. We are going to now pivot over to your questions because I know we probably have so many questions in the room. So don't be shy. Put up your hand if you have a question and you'd like to get the microphone. And we will start here in the red sweater. That was very game show hosty of me. In the red sweater.
I have a question regarding nuclear power. You said about 6 to 8 year life. What is the price of the unit and the minimum break-even price of the electricity?
So it's designed for 60 years, 60. Yeah, 60. So it's a 60-year life. Yeah. That changes the equation quite a bit. Yeah. You know, it's interesting to see as we talk to different potential customers across the globe, what we find is that the cost will vary significantly depending on location. The modules don't change much, but the construction crews and that kind of thing. So as the Chief Technology Officer, I've been told by my CFO not to share cost. So I can't give you a number per se, but you know, typically nuclear power, when you think about the number of modules, so we look at 4 modules, 6 modules, or 12 modules. So a 12 module plant is almost a gigawatt of power. So if you look at it that way, the cost will vary significantly. So sorry, I can't give you a number.
That's great. Let's go to our next question over here with the gray blazer.
Hi, I'm Deepika from Berkeley National Lab. My question is to Sujay. So you were talking about microelectronics and memory and how much data is generated. I'm a biologist, and I think DNA is a very nice chip that encodes and stores a lot of data. Is there ever a discussion or thought that might cross your mind or somebody that if that can ever be leveraged or used in storing data?
Yes, absolutely. We have a professor, Grigory Chikomarov. I think he spent his postdoc at Caltech, but he's a professor at UC Berkeley looking exactly at that, using DNA, for storage and for interesting computing paradigms. Yeah.
Great question. There was another hand over. Yes, here we go. We got the microphone. Thanks.
Hi, I'm Charu Vardarajan, also from Berkeley Lab. So this is a really great set of presentations, and all of you are working on applications that touch deeply on society. And there's a sort of a benefit, but also perceived risks of maybe if your technology or a product isn't quite what people think, like nuclear waste, for example, or safety. AI is definitely sort of ways in which people perceive risk for AI, or even medical drugs. I'm curious how you approach your balance between when you think your product is ready for mass market. How do you make those decisions as you're sort of moving along for this is ready, this risks, the benefit to society is more than the risks that we could face if this were not to work. I'm just wondering how you approach that, and exploding spaceships are put at risk, right?
Yeah. So I think that's a great question. It brings it back to the humanity aspect of all of this. Obviously, we all work in science and technology, but I think all of you mentioned that it's really for the greater of humanity. So who wants to tackle that question first in terms of, when do you know you can roll this out, and when do you think society is ready for it?
Maybe I'll go ahead and start. Yeah, at least for the nuclear industry as a whole, the Nuclear Regulatory Commission is extremely rigorous in terms of moving a new product onto the market. Extremely rigorous. Just to give you an example, we spent about $500 million developing all the information you need for the application. So we had to do a lot of design work up front before we submitted a high quality application to the regulator for them to review it. Then we spent another $70 million in fees to cover the cost of the review. And then internally, we spent another $200 million responding to regulatory questions. We wound up submitting close to 2 million pages of information. It is the most rigorous process in the world because of the concern and the requirement for safety. Now, we have a very simple design. It's a very elegant design. It's extremely safe. I can say it's one of the safest designs that the regulator has ever reviewed. But we had to go still through that entire process. So that's something that's being looked at right now in terms of regulatory processes. But we cannot go forward with a product that's not safe and demonstrated to be safe unless the regulator approves it. So that's how we deal with the risk part of it.
Yeah, I'll jump in. It's actually a really great question, nuanced and complicated. Our industry is also extremely regulated. So there are regulators that decide on things like health and or on safety and efficacy. That would be like the FDA. And there's other regulators decide, should we pay for it or not? And it's not the same system around the world. It's a different system in every country around the world. So to actually bring something to reality, you have to be able to satisfy regulators. And for the most part, regulators are biased to be cautious because they don't want to end up on the front page of the New York Times saying, look, you approved this thing that's no good, and you find out after the fact. And so their bias is to be cautious about this. Now, separate from all that, some companies would operate under the moat because of the financial realities, would say, as soon as we get approval, we're going. But where do your own standards come in? Or are there times when you're going to have a standard that might be even higher than the standard of the regulator? And that could and should be the case in something like healthcare. And there you go into a softer world of like, okay, would I use this on my family? And those kind of simple questions.
Yeah, somebody mentioned spacecraft breaking up over small island nations recently. So our launch especially is also a very highly regulated industry. And when we launch something like Perseverance, which has plutonium in her tail, it's very, very highly regulated. There's a whole extra level, as well there should be, because launch vehicles are highly energetic, and that word we don't like to use, exploding, is also possible. So I think, I mean, the whole thing's a risk conversation, right? And I think I worry that as not just as a nation, but sort of humanity, we don't talk very clearly about risk and benefit, right? It's a subtle conversation to be had. And so I think, there's probably a lot we can all do as critical thinkers, as scientists and engineers, to bring more nuanced conversations about risk to the world, because in some cases it might make sense to lean forward and take more risk, right? If your family is suffering with someone with a disease, you might be willing to take that risk. And so to me, there's an interesting opportunity at the moment to, as sort of the regulatory environment is becoming much more in public view, to try and have that conversation. I hope we can have nuanced conversations about it as we go forward.
Yeah, just to follow up on what Laurie said, I think that relates to the part of the mission of the NAE, right? Where we need deep scientific technical knowledge, expertise to inform the regulators, the policymakers, the lawmakers. Otherwise, how are they going to make the right decision balancing risk? Manage risk for the benefit of the country. And I think this week there was the AI summit in France, and different countries had different tolerance to risk with regard to AI. So maybe with regard to artificial intelligence, I think definitely we need to engage humanists as well as the scientists and the computer scientists and the engineers in advancing the forefront of AI. I really like this mission of engineers to work towards advancing, benefiting humanity. Now, humanity has multiple meanings. Humanity means all of humankind. It also means the quality of being human, like we want to preserve and benefit humanity in that sense as well. And also humanity means like what is the essence? What are the qualities of humans, right? Kindness and like empathy and things like that. Those are all aspects of humanity that we should be thinking about benefiting when we are advancing AI. And this is why we need to collaborate not only with engineers and computer scientists, but the humanists, the social scientists, the business, policymakers, business people. It's just highly complex systems require more interdisciplinary teams. But we don't want to slow down progress either. This is one thing because technology advancement, it is a race, right, between countries. And so we don't want to bog things down with regulations, but this is where we, like scientists and engineers really need to collaborate, reach out proactively to people and work with people in government. And that speaks to the mission of the NAE.
Great points. I think it's all in alignment with it. It's a team sport, across science and engineering, but across so many other sectors internationally as well. There's so much collaboration that's needed. Really great question. We're going to take this question right here. Yes. Oh, sorry. I didn't realize that. You already got the mic. There we go.
Yeah?
Go for it. Yes.
My name is
Thanks.
Boris. I'm here from UCI, electrical engineer.
Okay.
I have a question about energy. I guess it's both Jose and Sujay for you. It's a fundamental physical problem here, right, of energy. And I really like the two curves that are about to intersect sometime in 2040, I think it was, or whatever it is. So, Jose is trying to lift the upper curve up, right? And we are trying in electrical engineering to, as you said, bend the curve. But there's one problem. So the metric we're using, to bend the curve, for example, in the digital world, maybe, let's say, energy per bit. So we're trying to reduce that by reducing, the communication cost of energy and et cetera, et cetera. But the problem is that have we seen in the last 70 years from scaling is at the end, people want more and more bits. Even if the energy per bit is lower, we want more and more bits, more functionality. And this curve will continue to rise. How do you see this as a philosophical question? How do you see this scale at all?
Yeah, that's a great question. Thank you. So I guess to summarize, if we make energy efficient, computing more energy efficient, people just want to use more computing, and the total amount of energy consumption is the same. But I think there is, I have to plead ignorance, but I think there's a difference between useful energy, the efficiency of energy usage. So if you make the computers more energy efficient so you don't waste the heat that's generated, this still is better than just generating heat and contributing potentially to global warming, So I think there's definitely, it's still worthwhile to improve energy efficiency of computing, even digital computing. And we know that there's some fundamental minimum energy needed to perform a bit of computing, and we're orders of magnitude away from that fundamental limit today. So there's definitely room for innovation. Maybe we can lower the total energy consumption of computing if we can exponentially reduce the amount of energy per whatever, what is the computing, petaflop, yeah. So I think it's we need innovation. This is why we're here, to inspire you all.
Yeah, that's a great question. Okay, our next question. Mm-hmm.
On solar cells, and nobody told us, the people that lived there, that they could catch fire. And it was absolutely terrifying. And not only the fires of lithium batteries, but then the micro metals that came out afterwards.
Right.
Why I'm telling you this is for young people to see a huge amount of innovation in dealing with disasters. I suppose you could also look at the wildfires and the innovation needed in every respect to deal with all these disasters that are happening.
Great. So I will pivot. I think that was some words of wisdom, but let's pivot that into a question of.
I could talk a little bit about having just
the wildfires we were just talking about.
Yeah, so we're at JPL. 210 of my colleagues lost their homes in the Eaton fire. I think we were the single largest impacted employer of the fires in Southern California this past week. or this past month. Sorry, time has stopped since the fires. I have no idea how long ago it was. I personally am displaced at the moment. My home was damaged and is in one of the neighborhoods that burned, but thankfully my house is still standing. So I didn't come first thing this morning because I went up the hill to see if it was still there after the rains last night. It's been quite the journey. And yeah, there was a battery farm somehow that burned in Altadena as well. And so I think this is it's a great question. And so it's really a life cycle. And I'm sure you could talk to how you think about the end of life of your reactors, right? Like you have to have a plan for that, and you have to have a plan for. It sounds like they're really designed for when something if or when something goes wrong. And so I think there's clearly more of that needs to happen. But I would also say, like, there's a lot of us that can. This is to me the power of applied science and engineering, right? Making sure that we are thinking about how do we leverage the great data that we're getting from our wonderful spacecraft to understand our planet better and help plan and prepare for disaster and help recover from it. There's so much more that we could be doing there. So yeah, I mean, your stuff was amazing there.
Yeah, exactly. We already have a decommissioning plan.
Right.
So we know we designed it so that you can actually remove the modules the same way you put them in. So I think but it requires forethought. You have to be thinking about 60 years down the road, what are we going to do with this plan?
Or in case of emergency, in case of a large earthquake, in case of a fire, like what are we doing?
Yeah.
That's right. Preparedness, and nobody ever wants to spend money on preparedness, but it's so important.
It's required.
I can say now after the fire came very close to JPL, and so, but we for decades have been getting ready for a night like that, and so we were able to defend the laboratory, and it's because of preparedness. It's so important.
It is, and I know in some of the other forums that we've hosted, we talk about, designing resilient technologies, and, there's a need for efficiency, but also just thinking about how our new technologies can be resilient in the face of new threats, no doubt. Great question. All right, wait, no, who has the microphone? I keep going to the hands and not the microphone. Oh, you do have the microphone. Yay. All right. Hand in a microphone.
Thank you so much for sharing your time with us. I'm Shreya. I'm a biomedical engineer at Harvard. My question is, how do you think about balancing high risk, high reward projects and low risk, known reward, especially as you take a team from you take a small team and you grow it and you scale to a big organization? How do you come up with those projects, strategically plan, and then excite your team the right amount?
Great question. Who wants to take on high-risk projects?
I'm sorry, I feel like I'm talking too much, but we should hear from others too. But we think about this all the time. I think it's a great point. So you had Perseverance, which is a multi-billion-dollar, probably too big to fail kind of mission, which we take years and care. I call those big missions, like Europa Clipper as well. Like they're like modern cathedrals. They're generational quests. They take 20 years from conception to build to fly to science, right? But then we stuck Ingenuity on there, the little helicopter, which I didn't really talk about today, which was done for 3 years and like no money and with a little scrappy team. And it's the same organization that did both of them, right? And I think it's so critical that we balance, that we always have, especially when organizations get large, that you have a portfolio of risk that you're dealing with. It's a great challenge for the organization, because once you learn how to get conservative and everything always works, you tend to want to use that hammer on everything, and that's where you run into trouble. But if all you do is take tons of risk, and sort of the Elon Musk model is take risk, fail, learn, go fast, do that. That works great on Earth. You only get to go to Mars once every 2 years. It takes 9 months to get there. That model doesn't work so well, right? And so there's got to be a balance depending on the application. And to me, it's one of the exciting things about working in technical fields is to really be constantly thinking about, are we balanced right on risk? Is there a place we can lean forward? Have we learned enough from the failure so that we can smartly take risk on the next thing?
I think it's a great question. I think it's a great answer. We used a couple of tools in that regard. Of course, both are good. Some of those things that are a little lower risk are definitely going to make an improvement, and some of the moonshots. 2 tools we tried to use. One was the power of focus, when you're in your high-risk territory. So if you're in an area that you have studied deeply and you understand more, you probably can tolerate more risk than when you're into an area that you've never been familiar with. It's one. And the other one is a very sophisticated strategy called shots on goal, which is not everything is going to make it. And you're going to keep that in mind when you're going in and knowing that if you really want to be productive and innovative, you're going to need more than just a couple ideas. It's really helpful to have a portfolio of ideas and then back the ones that deserve it, et cetera, along the way. And those are tough questions, but simple tools. All important. Probably one of the more difficult things you do is like, when do you stop? People ask us all the time, oh yeah, people should just, they're so vested that they just follow ideas too long. But then again, we know how many good ideas faced failure after failure and people just fought their way through it. And so those decisions are tough ones. And I would say this is where you go spend your time to really get deep.
Yeah, great question. And I think there's a piece in the communication and expectation setting too. I know on some of these high risk things, there's expectation set of like, this is a test. If it works, like we will all be surprised, and giving people the space to understand that this is high risk area and we're doing some big, bold stuff here and have some patience. Great questions. Next question. Yes.
Hi, I'm Karthish Manthiram. I'm a chemical engineer at Caltech. I think two words that stuck with me from this morning are modularity and reusability. Modularity from what Jose described on SMR, and reusability from what you mentioned, Lori, on rockets. And I was wondering, Mike, if in the context of healthcare, when you look at modularity and reusability, do those stand to deliver on the promise of cutting cost in that context as well?
Yeah, it's a really good question. Modularity is challenging because in healthcare, we like to say, if you follow a pathway, we have evidence that says you will get this desired result. And if you make it modular to the point where you're going down a pathway that no one's gone before, then you have no evidence to be able to support it. And we get really uncomfortable in medicine if we don't have proof that we're going in the right way. So modularity gets a little bit difficult. And we need to be more sophisticated to be able to handle that. Reusability, obviously key. It's funny, it depends on the country and their tolerance for risk. If they don't have the money, they take things that we would never reuse in a wealthy place like the US and reuse it only 5 or 10 times in those places. Now, could you make that a reality such that you didn't have so many one-time disposables? Yes, you could. But then you're into this interesting trade-off, like how much time should I put into reusability as opposed to transformation of the entire practice, which sometimes could be more fruitful. So those are really important, but tough to think through when you're deciding how to use it. Great question.
Great question. So at this point, we are wrapping up. Unless you want to extend, I think we're going to be wrapping up. So I just want to acknowledge how many wonderful questions there have been so far. And I really hope that this conversation continues as we progress into lunch and throughout the day. As you know, in the afternoon, there's going to be breakout sessions subdivided in these different areas where you can keep asking those questions and having these dialogues. And I think the last question will come from me, which is, first, I just want to say thank you to our panelists for being here today and for sharing so much insight into your respective industries. But I just want to give each of you an opportunity just to give a little bit of inspiring words to our early career engineers out here as they go back into their respective fields and respective workplaces and are on their path of innovating in their own unique ways. So who wants to start? We'll start with Jose. How about that?
Sure. No, I guess I would say really pursue your passion. I think that's it keeps me going. I'm still having fun after all these years of working with this design. So I think that drives you to go into the office every day, to go into the lab, and to do creative research because it's your passion.
Yeah, I agree with that. It's so important. When you find, it takes a little time to find it, doesn't it? But when you find that thing that makes you excited about what you're going to do every day. The best in you comes out. And also just the surrounding yourself with people that maybe are a little different than you, right? Because this is where innovation comes from. When you're exposed to people that just think a different way, then wow, magic starts happening along the way, and continually see that.
You stole my word, which is magic. Yeah, I'm a big believer in magic teams, and if you've been on one, you know what that means. And if you haven't yet been on one, go find your magic team, because there is magic that happens when a group of people work together on trying to solve a ridiculously hard problem, and just knock down that one issue at a time until you're like, hey, we did it, or hey, we've made a huge amount of progress, and there's real power in that. The other thing I would just say is we are in a moment of where the ground feels pretty shaky beneath lots of our feet. And just to know that, we have built a resilient system for discovery, for innovation, for advancing in this country. And I believe we will come through this time if we work together. And, there's always ways to improve it. I think there's opportunity to do that right now. And let's work together to take this opportunity and make this system better, hopefully to support all of you in having really long, productive careers. So don't lose hope.
I agree with everything that has been said. And in addition to pursuing your passion, I think share your passion. We want to inspire the next generation of talent. I mean, technology, we all have roadmaps, right? 10, 20, 30 years. And some of us are thinking about retiring within 10, 20, 30 years. So inspiring the next generation, that's something I think we should all be doing, telling our story, but also celebrating our successes. Why don't we elevate and engineering, celebrate like the impact that we have? And when we succeed with a diverse team, like why don't we highlight the contributions of every single member of the team to just show people that they can become engineering innovators in the future? So I think that's something I'd like to say in addition to all the wonderful things that have already been said.
Wonderful, wonderful. So thank you to our magic panel, and we encourage you to go out there, find those teams, build that magic, keep innovating. So thank you, Sujay. Thank you, Lori. Thank you, Mike. Thank you, Jose. And I'll turn it over to Al for next steps.
Yes, well, thank you all.